Thank you. That'll be helpful.
Yeah, sure. Trying to. Mostly it's negative. Mostly all this working from home and teaching online has a lot of negative consequences, but the positive consequences are everything can be stored and watched later or read later. So that's a benefit. Before I get started, are there any questions?
Yeah, I had a question about like the homework and the homework format.
Uh-huh.
So, basically, I was on Wiley last night. I was trying to do some of the homework, and like there's like a show work option, right? That has like it wants us to like kind of draw on like a whiteboard on screen, like what we did,
Okay.
and I just like just as a little bit of feedback, I found it like kind of difficult to do because like my computer was like on a trackpad, and and it took me like 10 minutes to like really sloppily draw like 3 like expressions.
Okay, yeah, I see.
Expressions. So I was wondering if there's like another way to like upload my like hand drawn work like from a paper or something like that in order to like save some time and also make it easier to read.
I don't have an answer to that question right now. I haven't taken a look at that that particular question, but I'll definitely take a look after this class and see what options there are. Yeah, if there's a class of problem that's difficult to do just technically in terms of what devices or resources you have available, then maybe I'll try to remove those problems and replace them with other problems that try to target similar understanding but don't require you to, I don't know, do something messy with a trackpad or something like that. So I can definitely try to be accommodating in that respect. I'll take a look after class.
Okay, cool. Thank you.
Sure. All right, any other questions? Okay, if there are no other questions, why don't I get started? So what did we do last time? So last time, we gave some examples of differential equations and a definition of differential equations. Our definition is basically that they're just equations, mathematical equations that involve derivatives of functions. And we discussed what it means to be a solution. Discussed what it means to be a solution to a differential equation. Right, and so just in words, the idea is a solution to a differential equation is a function such that when you plug it into both sides of the equation, the two sides are always equal for any value of t, if it's a function of t, for instance. So yesterday we were mostly dealing with functions like y of t, where y of t was supposed to be the velocity of a ball or something like that. And we discussed kind of the notion that solutions ought to come in families, or there ought to be, right, so another point is solutions ought to come in families, and they should be parameterized by initial data. So if you remember the problems that we were doing last time, I don't forget what the general form of the solution was, but it involved this constant t that could be pretty arbitrary, right? There were functions y of t that we wrote down, that had some constant t, that constant c could be anything, and that function would still be a solution to the differential equation. And I mentioned in the context of the problem that we were working on, that coefficient, or that constant c, corresponded essentially to some data at the beginning of the problem, namely, how fast was the ball traveling initially? What is the initial velocity of the problem? So this idea of initial data is an important one. So maybe I can remark a little further. Solutions to a differential equation should not be unique, in the sense that there should be a whole family of functions that satisfy the differential equation. However, one could hope that you get unique solutions to a differential equation upon specifying some initial data. So for instance, well, we'll get to some kind of specific examples later, but something that we might look for would be what's called an IVP, or initial value problem. And this would be some differential equation. Say, I'm just pulling something out of a hat here, but something like dv of t over dt is equal to v of t minus 1, or something like this, right? This would be a differential equation. And then you also want to specify some initial data, like v of 0 is equal to 4. So here is the differential equation. There are going to be a whole bunch of functions that satisfy or solve this differential equation. So there's not a unique solution. But one could hope that upon specifying this additional data of an initial condition, that maybe this has unique solutions. Okay. And then one last thing that I want to mention is that often solving a differential equation is very difficult. Can be very difficult. So what I'm about to introduce is a way of working with differential equations that doesn't immediately involve finding a solution to the differential equation. So this brings up the idea of a slope field. And if you've gotten started on the homework that first of all, has everyone at least been able to access the Wiley Plus? Are there any further issues with accessing the website? If there are no further issues, then I have assigned one homework due on Monday. And if you've taken a look at that homework, you've already been kind of introduced to this idea of slope fields. Okay, so let's get into it. Let's take an example. So given a differential equation like dy dt is equal to 100. Well, let's do 10 minus 2y of t. One way to try to understand what's going on here is to immediately try finding solutions to this differential equation, namely find functions y that satisfy both sides. But we can do something easier, kind of an easier first step. Any possible solution would be some function y, which is varying in t. So just graphically, if I set up a t-axis, and then I set up here some what do I want to call this? X-axis, I guess. But really, the point is that y of t ought to be some function here. Y of t ought to be some function that depends on t. And the point is, this differential equation, dy dt over 10 minus 2y of t, it's forcing some information on us. Can anyone tell me what information this is giving me?
Just the slope.
Yeah, this is giving me the slope of the tangent line to the function y of t for a given y. So for instance, let's say I don't know. Let's say that this is some putative function. We say y of t. I hope that this is a solution to this differential equation, and then I compute. Let's say that at time t is equal to 0, y of t is equal to, I don't know, this looks like 5. Y of t is equal to 5. This is just kind of as an example. Then this equation would say that 10 minus 2 times y of t times 5 is 0. So the slope of the tangent line to this function when y is 5 has to be 0, namely this thing right here. And indeed, it looks like it is 0 at 5. So I could try to guess that maybe this is a solution. Let me go a little further. So the first thing that we could try to do, and this is the entire idea behind a slope field, is to make some sort of graph, or make a graph of slopes out of dy of t dt is equal to 10 minus 2y of t. So in particular, let's say when y of t is equal to 0, then that forces dy dt to be what?
10.
Yeah, 10. Just plugging in. So what this is saying is that at the height y is equal to 0, namely along this line, here's the 0 axis, then the slope has to be a positive 10. So I'm going to kind of put these very steep tick marks along here. How about when y of t is equal to 2? What is dy dt forced to be?
Six.
Yeah, 6. So at height 2, the slopes are lower. I don't know, 6 maybe looks kind of like this. And how about when y of t is equal to 4? Well, then dy of t dt is going to be 2. So here at 4, the slopes are quite shallow, 2. And then at y of t is equal to 5, we have something very special that's happening. Dy dt is going to be 0. This is all stuff that I'm reading off of the just the differential equation itself without any solution. And then if I go past, like y of t is equal to, I don't know, 6, then I get dy of t dt is equal to -2, right? So all the way up here at 6, here we have negative slopes. Okay. Now, the point is that any solution y of t to the differential equation must be tangent to the slope field at each point. So this already gives you some sense of what the solution should look like, even if you don't have mathematical expressions for them, right? We can see that a solution, and when I draw any particular solution, that corresponds to some initial data, right? Some initial data, for instance, what is y of 0 tells you where do you start along this axis. So let's say that we start down here. This corresponds to some solution with y0. Y of 0 is equal to, I don't know, this looks like -5, something like that. Then it looks like the solution probably looks something like this, right? And I know that no solution to this differential equation can ever look like this, because at this point, the slope of the curve is not tangent to the tangent line that is forced on me by the differential equation. So never happens. But some other solution could look like this, for instance. Then there's a very important solution to this differential equation that we can already see, and that's this solution. So we can already see. Can you read this? Oh, it's kind of the edge. One explicit solution, namely y of t is equal to 5, the constant function 5. All we need to do is check that this satisfies the differential equation, and indeed it does, because dy of t dt is equal to 0, and 10 minus 2 times 5 is also equal to 0. So we have a very, very special solution, a solution that isn't varying in time. Okay? So this is called an equilibrium solution. The solution that doesn't depend on t. So if this differential equation is modeling something physical, then these equilibrium solutions make a lot of sense. So for instance, this differential equation is reasonably close to the differential equation we wrote down for the velocity of a falling ball around sea level. And what this equilibrium solution here is expressing is that there's a particular speed where if the ball starts off at that speed, the speed will never change. The ball is falling at a totally constant rate, and the forces of gravity and the force of air resistance are kind of equally balanced. In another very physical situation, if you wrote down a differential equation that studies the motion of a pendulum, so then you'd think of theta of t, right? You'd think of this kind of the pendulum. If the pendulum swings this way, then we can call this theta 0. This is angle 0, and this is like 45 degrees, and this is -45 degrees, right? So most equations of motion will involve the pendulum swaying back and forth, right? So this is a solution that's varying in time. But for any pendulum, there's a reasonable solution where the pendulum just stays straight down, where theta of t is 0 for all time. That would also be an equilibrium solution to the equation of motion for a pendulum. So what I want to say is that these equilibrium solutions are very important, they're very useful, and if your problem corresponds to something physical in physics or biology or chemistry, they correspond to kind of important notions in those fields. Any questions on what I've done thus far?
Yeah, but one question. You said that
Sure.
an equilibrium solution is independent from t, right?
That's right.
Okay, thank you.
Yep. So an equilibrium solution like this one is a function of t that doesn't actually involve t at all. So equilibrium, so maybe as a definition, an equilibrium solution is constant in time, in t, in the variable t. Oh, you can't read that, sorry. Okay. Any other questions on this? One more very important note. Mathematically, slope fields are easy to produce. Because all you're doing is checking some explicit equation at a bunch of points. So computationally, it's very easy. It's very easy for a computer to produce a slope field. It's much easier than actually solving the differential equation. And here by solving, I mean finding a family of solutions such that you get basically all of the solutions in that family. Here we found one solution, but it's kind of it's simultaneously a very interesting and also very boring solution, right? That's kind of an oxymoron, but that's how it is. Okay, so it's for these reasons that a slope field is very important. And for a lot of differential equations that people encounter in real life, like for instance, the Black-Scholes equation in economics, there is no known solution in terms of just functions. You can't write down an explicit solution in terms of functions. So what people in the 90s in the stock market did is they developed computer algorithms and models to produce slope fields associated to that differential equation so that they could locally get an idea of what the model was saying at any given point, in the same sense as looking at this slope field tells you what a solution near here ought to be doing. And then they would make computers make purchases and whatever, and that's all very interesting. But the point is that often, like in many real world situations, you don't solve the differential equation. You just produce very detailed slope fields that give you a very good impression of what's going on with the differential equations. This is a useful technique, not just mathematically, but also much more generally. Okay, let's look at one more slope field really quick. And it'll be a very simple one. Let's do the slope field that looks like this. So slope field associated with dy of t dt is equal to y of t minus 1. So here the slopes are just extremely easy to read off. So let's say this is 0. Well, at 0, the slopes are -1. At 1, the slopes are 0. So 0 slopes along here. At 2, when y is 2, then the slope is 1. And at 3, the slope is 2, so slightly steeper. I really lose all ability to differentiate between a slope of like 3 and 6. I draw them like the exact same. 4, a little steeper. Okay, and then if I go to -1, it's -2, right? So a little more negative than what I had above. Okay, so essentially we're getting a very similar picture than we did last time. We can already see an equilibrium solution. Where's the equilibrium solution? Or what is the function which gives me an equilibrium solution?
Y
Y
equals 1.
Yep, y of t is equal to 1 gives an equilibrium solution. So if it's a solution, it's obviously an equilibrium solution because it's independent of t. And then you just check both sides. Well, d over dt of 1 is equal to 0, and 1 minus 1 is equal to 0. So indeed, it's a solution. So There's going to be some solution that I can draw right here, the equilibrium solution to this differential equation. And then we can already see what the other solutions look like. They look something like this. Well, not quite. Something like that. Or if they have a slightly different initial data, maybe they look like that, right? So here are examples of me trying to sketch a solution to this differential equation. Things like this, okay? So it's important to note already that even though this differential equation, dy dt is equal to y of t minus 1, is very, very similar to this differential equation that we had over here, dy dt is equal to 10 minus 2y, they actually are showing us very, very different behaviors in terms of their long-term solutions. So this sort of model right here, we introduced as coming from a falling body that is subject to both gravity and air resistance. And all the solutions seem to be approaching one value as time goes on, right? All the integral curves, these curves that look like solutions and whose derivatives are equal to the slope field at each point are called integral curves. All these integral curves seem to be approaching 5 here, which corresponds, if you view this as a model of something falling, this is essentially saying that 5, whatever meters per second or something like that, is going to be the terminal velocity. So no matter what speed you drop something or throw something at, it will eventually approach this stable terminal velocity. This is a very different behavior from what we see here, even though the functions are extremely close to each other. The behavior that we see here is if you start slightly above this equilibrium solution, all of the solutions explode. So this is actually an extremely simplistic population model in which if you start above a certain equilibrium point, then the population will eventually explode, like rabbits in Australia or something. And if you start below a certain equilibrium point, then your population will essentially go to these very big negative numbers. So this obviously isn't very realistic, but maybe one could interpret the decay of these solutions as the population is dying out, say. What do I want to say about these slope fields? Yes, they very similar looking differential equations can have different slope fields. The slope fields tell you quite a bit about the long-term behavior of your solutions. And the last thing that I want to point out is that the equilibrium solutions kind of separate these solutions into different regimes, right? So for instance, in the falling ball differential equation, the equilibrium solution separates the solutions that start off below. So these initially have a slower velocity and then they speed up to the terminal velocity, from the solutions where the ball starts off being faster and slows down to the terminal velocity. So the equilibrium solution separates two different regimes where the behavior is different. Here, things are speeding up. Here, things are slowing down. And it's the exact same case in this different model. The equilibrium solution is separating the solutions into two regimes. In one regime, where the initial data is greater than 1, right? Anytime that you start greater than 1, the population is going to explode. And anytime that you start off with something less than 1, which corresponds to a negative population, which isn't very sensible, but nonetheless, we can still talk about regimes, then here, the population or the quantity is going to be decreasing very steeply. So this idea of equilibrium solutions breaking up your solutions into different regimes with different behavior is a valuable one. Okay. Any questions about these slope fields that I've discussed?
Can you have an equilibrium solution break like solutions into more than two regimes? And like, what would that look like?
Yes, you can. There are definitely differential equations that we'll study pretty soon that do that. Here's an example of such a slope field. You would need essentially, in the most simple case that we'll see, you want like two equilibrium solutions. For instance, if this is some polynomial, like y of t squared minus 1, let's actually try to, yeah, this is a very explicit example that we can do. dy of t over dt is equal to y of t squared minus 1. Oh, wait. About this. Yeah, okay, good. This looks like a polynomial in y that we can factor. How do we factor this polynomial in y?
Difference of squares.
Yeah, exactly. So this is just going to be equal to y of t minus 1 times y of t plus 1, if I have remembered how to factor correctly, which I have. From expressing this differential equation in this way, I can see that there are going to be two different equilibrium solutions. One equilibrium solution where y of t is going to be equal to 1, corresponding to when this is 0, and one equilibrium solution when y of t is going to be equal to -1, corresponding to when this is 0. And one can check that both of these are equilibrium solutions because the derivative of a constant is 0, and then plugging in y of t is equal to either 1 or -1 will also make this side 0. So what you see is if this is our, where we're going to plot our slope field, and this is 0, you're right, 0, then at -1, we're going to have a equilibrium solution, and at 1, we're going to have an equilibrium solution. And then we can start plugging in points. For instance, what happens when y is equal to 0? Well, when y is equal to 0, the slope is -1. So my slope field is starting to look like this. And when y is equal to 2, 2 squared minus 1 is going to be 3. So at 2, my slope field is steep. And when y is equal to -2, once again, my slope field is going to have slope 3. So here I also have slope 3. Without drawing too much more, what we can already see is that these two different equilibrium solutions are separating my solutions into 3 different regimes. There's going to be one regime up here where my guess is that we're going to see things explode like this. There's going to be another regime in between the two, which probably is going to look roughly like this. Solutions are going to look like they're transitioning from being close to 1 to being close to 0. And then we're going to have one last kind of regime of solutions where these things are going to be approaching -1 from below. So we're going to see, I mean, we're going to do examples with these, but here already is an example where several equilibrium solutions lead to different, like here, 3 different regimes of behavior. Okay. Any questions on this quick example that we've done? That's a good question. And notice an important fact is that nowhere in any of this analysis did I ever actually solve this differential equation. The equation for this solution is going to be an interesting function. I didn't solve for it. I can see what the overall behavior looks like, but I never did the hard work of actually solving this differential equation. That's what makes these slope fields so valuable. It's kind of like, you know, when you were doing calculus, a good rule of thumb is try to sketch the function that you're trying to take the derivative of, right? If you can get some sketch, you can try to make some progress without actually doing the hard work. Right, so this is kind of like a sketch. Okay, any last questions? Okay, moving on. So slope fields are an important technique that we want to use and gain understanding from, but we also ought to actually do the hard work of actually solving some differential equations. So let's actually solve the differential equation dy of t over dt is going to be equal to a times y of t minus b, where a and b are constants. So notice that most of the differential equations that we've discussed so far have been of this form, right? This differential equation, 10 minus 2y of t, was of this form. This differential equation up here, dy dt is equal to y of t minus 1. This was of this form as well. So we're kind of, we've been working with this class of differential equations during these 2 days. Let's actually solve this differential equation. And as an additional point, remember that we kind of expect this to come in families. So we should specify some initial condition or some initial value. Specify some initial value or initial condition. So let's just say that y of 0 is equal to y0. It's a good way to just pass off doing any work right now and just say, I'm putting off the problem of telling you what the initial data is, but it's just going to be some constant, some number. Okay, so the overall technique that we're going to see again and again in different guises is that one way to solve a differential equation is to get one side of the equation looking like the derivative of a function y, or some function involving y and t, and then have the other side only involve t's. That probably wasn't a very helpful comment, but we can do something explicit. What I mean by that is we should get all of the y's on one side. This is a way to start. So from dy of t dt is equal to a y of t minus b, we should get dy of t over dt is equal to, let's try to factor out the stuff involving y of t, and so that we're left with just constants. So then we should get is equal to y of t minus b over a times a, right? And then let's divide by the stuff involving the function y. So divide, we get dy of t dt over y of t minus b over a is equal to a. Now, I just want to say kind of what we have achieved at this point. What we've gotten is we've split up our differential equation so that one side is only a function of t, and the other side involves the function y, and hopefully we can recognize this function as coming from a derivative of something. Does anyone know a situation from calculus where we get derivatives that look like this? You have a derivative of the function over that function minus a constant.
Log, like?
Yeah, natural log. Natural log has derivatives that looks like this, right? If you think about a chain rule, so as an aside or a reminder, chain rule, if I look at d over dt of natural log of f of t, this is going to be equal to 1 over f of t times df of t, d over dt f of t, right? So that's of the same form that we're dealing with over here. So what we can do is we can rewrite this whole left-hand side as the derivative of a natural log. So this whole differential equation becomes d over dt of natural log of the absolute value of y of t minus b over a being equal to a. Why do I introduce the absolute value sign?
Because the natural log cannot be negative.
Exactly. I want to be able to understand solutions where y of t is less than b minus a, so that this whole term is negative. I still want to be able to understand the differential equation when y of t is some negative number, say. So I need to have absolute value signs appearing. And now, if I've written my differential equation as a derivative just in t of this function being equal to a, the natural thing to undo this is to take an antiderivative with respect to t. With respect to t on both sides. So from the fundamental theorem of calculus, if I take the antiderivative of a derivative, I will just recover the function on the inside. So over here, I just get, well, that's not from the fundamental theorem of calculus. That's just the definition of antiderivative. But anyways, we'll get on this side the natural log of the absolute value of y of t minus b over a. And this is going to be equal to the antiderivative on this side, which is going to be at plus some constant c. Right? So we're well on our way to actually solving this differential equation, because we're very close to, like, already this expression doesn't involve any derivatives of our function y. It only involves our function y. And what's left to do at this stage is write it out so that the y isn't hidden behind all this natural log and summation and absolute value. We just want y of t is equal to some expression in terms of t. And that's not so bad. If we want to continue solving, we raise both sides. You say e to the left side is equal to e to the right side. So e to this is equal to e to this. And what we get is absolute value of y of t minus b over a is equal to e to the at times e to the c. Any questions on this collection of steps so far? Okay. What do we do when we have a natural log? How do we get rid, or sorry, not natural log. How do we get rid of absolute value signs?
It becomes equals to plus minus e to the power of at times
Exactly.
c.
You say, well, first assume that the interior value is positive and see what you get. Then assume that the interior value is negative and see what you get. And lastly, we'll see what happens when the interior value is 0. So case 1, if y of t minus b over a is greater than 0, then this equation just becomes y of t minus b over a is equal to e to the at times e to the c. So my solution of this differential equation is just y of t is equal to e to the at times e to the c plus b over a. Okay. Case 2. If y of t minus b over a is less than 0, then that means that the absolute value sign, the action of the absolute value multiplies the inner expression by a -1. So what I really get in this case is that b over a minus y of t is equal to e to the at times e to the c. And if we solve out for this, we'll get that y of t is equal to negative e to the AT, e to the C plus B over A. Sorry, writing next to this lamp is kind of difficult. And then in the last case, what if the interior is 0, if y of t is equal minus b over a is equal to 0? Well, this is kind of a different case, right? If the interior is equal to 0, is e to the at times e to the c ever equal to 0?
No.
No. So we've run into a slight case where we can't write the solution in this form, but what we can do is we can write that y of t minus b over a is equal to 0 times e to the at, e to the c. Or in other words, y of t is equal to 0 times e to the at plus b over a. Okay, so these are the cases that we're looking for. These are the regimes. All of these produce solutions to the differential equation that we're interested in. And it turns out that the nicest way to think about this is as follows. This e to the c, when we derived this e to the c, well, c is always some real number, right? at plus c, c is a real number, so e to the c is always some positive constant. So if e to the c is some positive constant, then you get this family of solutions where y of t minus b over a is greater than 0. But if we allow this constant to be negative, then we get this family of solutions. And if we allow the constant to be 0, then we get this family of solutions. So the point is, the derivation of finding all the solutions led us to these 3 different expressions, but all these different expressions can be subsumed into the one expression, y of t is equal to, I'll write it as c prime, some constant, times e to the at plus b over a. And now, when c is positive, I can set c prime equal to ec. When the constant is negative, then it's equal to some negative e to the c. And then this case is when c prime is equal to 0, right? So this is going to be the general form of the solutions. And there's one more piece of data that we want to include, which is that we should recall that we want to include the data of initial condition, right? Here, this is a whole family of solutions, and the family depends on this parameter c prime. So let me write this again. So what we've got here is we found this family of solutions, y of t is equal to c prime e to the at plus b over a. Let's say that we want to remember that we specified some initial data. So y of 0 ought to be equal to y0, this constant number. But y of 0 is equal to c prime e to the 0 plus b over a, or this is just equal to c prime plus b over a. So what we ought to do is we ought to set c prime equal to, equal to y0. Thus, setting c prime equal to y0 minus b over a yields y of t equal to y naught minus b over a times e to the at plus b over a. And this is going to be, I mean, mathematically, this solution is really no different from this solution. We have just written it slightly differently so that for whatever initial data y0 you want to plug in, say you want y0 to be 1, Well, you just plug in 1 into this formula, and then you get a solution to the differential equation with initial value 1, y of 0 equal to 1. Okay, so this is the general form for the differential equations that we were exploring yesterday involving a ball falling near sea level. This is also the general form for the solutions of something like dv of t over dt is equal to v of t minus 1, or dv of t dt is equal to 1 minus v of t. All of these different differential equations can be solved using this formula. Okay. Any questions on that? No? No questions? What this does do is it allows us to kind of loop back to these particular differential equations. Let me really briefly draw the kind of slope fields for these two differential equations. The slope field here, both of these have a equilibrium solution at 1. And then here, the slope is positive when v of t is greater than 1. So we're going to have things that look like this. The slope field here looks like this. And we're going to have things that are kind of going up like this. And below, things are going down like this. And then here, it's going to be the opposite. Here, the slopes are negative above 1 and positive below 1. And now, instead of just having sketches of the solutions or ideas of what the solutions ought to look like, we have extremely explicit descriptions of what the solutions are. Here, v of t is equal to v0 minus 1 e to the t plus 1. And here, the solutions look like v0 minus 1 e to the negative t plus 1. And so we can explicitly write down what these curves are. These curves are exponential curves, either positive or negative and shifted by a 1. And here, these are exponential curves e to the negative t. So this behavior is exactly what you expect for a function e to the negative t to look like. So we're kind of going back and forth between the actual description of the solutions and what they look like on the slope field. Any questions here? No questions? Everyone is tired of me talking about slope fields? Okay. I would like for you all to do 1 or 2 brief examples. These are pretty similar to what you've seen on the homework, if you have looked at the homework. So I just want to be able to have you all work this out, and so we can discuss. So as an exercise, so the field mouse population, P of t, satisfies dp of t dt is equal to p of t over 2 minus 450. Let's just assume that the population satisfies this differential equation. When does a starting population of 850 field mice go extinct? So I'd like for you to work on this for maybe 3 or 4 minutes, and we can discuss and move on.
Hi, could you lower it a little bit?
Lower this?
Just a little bit. I'm sorry, go up a little bit. There you go. Thank you.
Sure. Oh, another important thing that I just want to mention, a non-mathematical remark. I used to make fun of my professors when they said things like that, and now I'm doing it. If you live in a time zone or are working in a time zone that is significantly different from Eastern time, please send me an email because I need to figure out a system for testing. If everyone is in a time zone that is nearby, then I can test in a narrow window. But if more than one, or actually probably if any students are in a very different time zone, then I'll need to have a different system for testing. So please send me that information by email. Are people done with this problem or not quite yet? Should I give you another couple minutes? Another minute or two, maybe?
Yeah, another minute would be good.
Yeah, sure. Just as another question, how are we doing on background noise on my end? Do you hear all the nonsense that's happening in my house?
No, it's fine.
Okay, cool. Okay, let's start kind of going over this a little bit. So we're given a differential equation which looks like, oh man, this is terrible. Now I need to, oh no, I have it here. Okay, so I'll just write it down again. dp of t dt is equal to p of t over 2 minus 450. This is exactly something of the form dp of t over dt is equal to a p of t minus b, where here a is going to be equal to 1/2 and b is going to be equal to 450. And we know that the general form of a solution to an equation like this is what I just wrote down on the other page once again. So I need to like y0 minus b over a. So p of t is going to be equal to y0 minus b over a e to the at plus b over a. Is that correct? So in particular, the solution p of t, my y0 is 850 because my starting population of field mice is 850. So I have 850 minus b over a is 900, e to the t over 2 plus b over a is 900. So this is my function for population with the given initial data of 850 field mice. And what I'm going to do is I'm interested in finding out the time at which this population is equal to 0. So I just set this whole thing equal to 0. Population is going to be equal to, this is negative 50 e to the t over 2 plus 900. And solving this out, I'm going to get, what's 900 divided by 50?
18.
18, perfect, thank you. 18 is equal to e to the t over 2, so we get t is equal to 2 times natural log of 18. And this is the point in time at which our experiment on 850 field mice ends in disaster and their colony dies out. Okay, great. Are there any questions on this, this problem, or is that reasonably straightforward after we have the general solution to differential equations of this type?
So if we were to like solve for this, do we need to show like the derivation of getting that initial equation where where is it? Like P of t is equal to y naught minus b over a.
This thing right here, this general solution?
Do we have, can we just use that as like like we just know, like we see that, oh, okay, this differential equation is in the form of like, you know, a times y of t minus b, and then just use that?
So the answer here is going to be essentially yes. This is kind of similar to when you're doing Calc 2 and you were doing integrals, right? Kind of complicated integrals. So there were a certain number of challenging integrals that you just had to memorize. For instance, the integrals involving like dx over x squared minus a squared, which were like the arcsine or arctan or stuff like that, right? So you definitely want to memorize a certain number of integrals, but on the exams, I'm going to be asking you how to take, you know, find differential equations, or in other words, integrate functions that you don't immediately recognize, and you have to do some work to get it into the right form. So it's going to be kind of like that, where it's good to memorize some solutions to some differential equations, but no matter what, you're going to have to do some derivations somewhere. The class is about these derivations, finding families of solutions to differential equations.
Okay.
Does that kind of answer your question?
Yeah.
Yeah. Okay, great. So this is essentially what the introduction was about. So we discussed what differential equations are. We discussed what their solutions are, how to check if something's a solution. We discussed a way to understand differential equations without finding their solutions, namely slope fields. And now what I'm going to do is kind of open the floodgates in terms of the classification of differential equations. The vast majority of these differential equations we will not touch in this class. I just want to kind of show the things that are possible with differential equations. And this is the material that's essentially discussed in section 1.3. So 1.3, classification of differential equations. How much time do we have? Oh, not very much time. Okay. So the first distinction or important point that I want to make is the difference between ODE and PDE. So ODE stands for ordinary differential equations. And PDE stands for partial differential equations. And essentially, this is going to be a question about whether the functions that we're interested in have one variable or several. So how many variables? In the examples that we've done, like dv of t over dt is equal to a v of t minus b, or even something like some polynomial p of v of t. Does it make sense when I write p of v of t for p some polynomial? Right? This is something like being equal to v of t to the fifth minus 10 v of t plus 4, something like this, right? This is a collection of differential equations that we could write down, where the functions that we're interested in are all functions of one variable. These are all functions of t, right? V is just a function of time. These are ordinary differential equations. An example of a partial differential equation is something as follows. For instance, this is an extremely important partial differential equation in physics and mathematical physics. This is called the heat equation. U is now going to be a variable, or U is now going to be a function of 4 variables, x, y, z, and t. And then the equation is partial of U with respect to t is equal to some constant alpha times partial squared of U with respect to dx squared plus partial squared of U with respect to dy squared plus partial squared of U with respect to dz squared. So this is a partial differential equation. You can tell that it's a partial differential equation, one, because I wrote partial derivatives everywhere, but more reasonably, because I'm taking derivatives in a bunch of different variables. U depends on 4 variables, and I've got derivatives in terms of each of those variables displayed here. So this partial differential equation dictates or controls how heat diffuses if you have, for instance, here we're dealing with R3, so 3-dimensional space. If you start off with some U0, this is some function equals U of 0, or sorry, x, y, z, 0. This is like specifying a distribution of heat at a particular time. When time is 0, then we have some function which tells you how hot each point in 3-dimensional space is. And then how the distribution of heat changes over time is governed by this partial differential equation. This is an extremely important partial differential equation that's very important to study. But we are essentially not going to deal with PDEs in this class. We're mostly going to be dealing with ordinary differential equations. Any questions on this? No? Okay. the next part of the classification will be systems of equations. So here the question is, how many functions are involved? And I'm just writing from the book here, not doing anything fancy. An example of a system of equations where there are more than one function that we're interested in are what's called the Lotka-Volterra differential equations. And these are given by dx dt is equal to ax minus alpha xy, and dy over dt, which is given by negative cy plus gamma xy, where x of t and y of t are populations of a prey species and a predator species. Right? So if you put a population of prey and a population of predators inside some enclosed area, the populations are obviously going to depend on each other. If you put 0 predators, then you expect the prey species to just flourish and grow and whatever. And then if you put, you know, very few predators and a bunch of prey, one could conceivably imagine that very few prey and a bunch of predators, maybe the predators eat all of the prey. So for a little while, their population grows, but then when there's no more prey, they have nothing left to eat, and then they die out as well. So these are two different functions whose behavior should be related to each other. Notice that I'm once again here dealing with ordinary differential equations because all of my functions are just depending on one variable, time. So this is a linear system, or it's actually not a linear system, but it's a system of equations, of ordinary differential equations related to each other. So here, a solution to the initial value problem would be functions x of t, y of t, such that x of 0 is equal to some x0, some initial population of animal x, and y0 or y of 0 is equal to y0. So you specify how many of the prey population goes into the enclosure and how many of the predator population goes into the enclosure, and then you need two functions which together satisfy this pair of differential equations. This would be a system of equations. And we will examine these. We will work with these. Any questions here? By the way, can you all hear me?
Yeah.
Yeah.
Yes.
Okay, good. I really would have no idea. Okay. Is this okay? Can someone give me a little bit of feedback? Is there anything confusing that I'm saying here?
No, like makes sense.
Okay, thank you. Okay, so another way that we want to kind of keep track of the different kinds of differential equations that we'll deal with is something called the order. So definition, the order of a differential equation is the highest derivative that appears. For instance, in all of these things that I've written for you, these are order 1 differential equations because the highest derivative that appears is a first derivative. However, where's the heat equation? the heat equation, this would be an order 2 differential equation because somewhere I'm taking the second derivative of my function. So more generally, we could write something like this. Some big function f, and then the variables are going to be t, u of t, u prime of t, u double prime of t, all the way up to u, and here this means the nth derivative of u with respect to t, equaling 0. So this would be, oh, I'm sorry, that's not visible, is it?
Thank you.
So this would be an example of an order n differential equation. And then you just make some function out of these variables, t, u of t, all the way up to however many derivatives. So some example of an n-ordered differential equation would be something like u of n of t squared times cosine of, well, let me just do something concrete. U of 3 times cosine of u of t second derivative times e to the u of t plus t equaling 3. Right? So this is some extremely complicated differential equation that I've written. What is the what is the order of this differential equation? What is the highest derivative of u that appears in this equation?
Is that a 3?
Oh yeah, it was not legible, was it? 3. Yes, this is an order 3 differential equation. Of course, I just use this upper notation, which I hope you're familiar with from calculus. Otherwise, I would have had to write d over dt, d cubed over dt cubed of u of t, this quantity squared times cosine of d squared over dt squared of u of t, right, et cetera, et cetera. So this is just a notation, but maybe here it's more explicit what the order of the differential equation is. Right? Okay, going further. Man, this quarantine is bad for the trees. Yes, linear versus nonlinear differential equations. Has anyone taken linear algebra or any linear algebra?
I had.
Okay, so not very many, though, it sounds like. Since I didn't hear a chorus. Of course, you're all muted, so maybe everyone chimed in and said, yes, I've taken differential equations, but since you're all muted, I didn't hear anything. Probably not the case. Probably there isn't too much linear algebra. That's okay. So let me write the following definition. An ODE, or a PDE, so a differential equation, say I'll write f of t, y, y prime, all the way up to y to the n. Here, y is understood to be a function of t. So really, I should have written like y of t, y prime of t, etc. Is linear if it is a linear function of the variables y prime, y double prime, all the way up to y to the n, but not t. I don't require linearity in t. I'm going to give two definitions of linear. Both are important. One is more important for this class, and one is more important going forward. The first one is more general, but perhaps less useful for this class. Linear means, oh, is there a question?
Yeah.
I cannot hear you. Hello? Could someone else speak up so I can ensure that I'm not having any issues?
Yep.
Okay, so I'm not having any issues. So I think it's on whoever was asking me a question. Might have be, yeah, if you type your question in chat, that'd be fine too. In the meanwhile, I'm going to keep writing. So either write it in chat or use your mic. The first definition of linear, does it have to be linear with respect to y? Yes, it does. Thank you. Very good. It does have to be linear with respect to y. The only variable that it doesn't have to be linear with respect to is t. So a priori, when you have a function on what's called a vector space, which we will maybe get a little bit to, linear really means two things. It means, and I'll write it down in these terms. So it should mean that f of t, if I have y1 plus y2 and y1 prime plus y2 prime, and all the way up to y1 to the n plus y2 to the nth derivative, this thing should be equal to f of t y1, y2, all the way up to y1, y1 prime, all the way up to y1 to the n, plus f of t y2, y2 prime, all the way up to y2 to the n. This is one property. Then the second property that we're going to require is that if I change all of these variables by a single constant, so namely f of t, cy, cy prime, cy double prime, all the way up to cy to the nth derivative, this should be equal to c times f of t, y prime, all the way up to y to the nth derivative. So this description of linearity has to do with the properties of a vector space. Namely, if you add two things, the functions just add. And if you multiply by one constant, then you can kind of pull that constant out. This is one and really the correct definition of what it means to be linear in a collection of variables. But the second definition, which is more useful perhaps for us, is there a question?
No, sorry, I was just coughing.
No problem. A second definition, which is more concrete for us, is that a linear differential equation will look like the following. It'll look like some function, an only depending on t, times y to the nth derivative, plus another function, n minus 1, depending on t, times y to the n minus 1 derivative, all the way down to plus a1 of t, y prime, plus a0 times y, or sorry, a0 is also a function of t times y is equal to g of t. So essentially, the linear part means that these terms, these derivatives of y, all appear on their own, and the possible coefficients only are functions in terms of t. They're never functions of y or y prime or any other thing. So in other words, if you remember polynomials, a linear polynomial will have your variables, and you can't raise them to any powers, and then the coefficients are usually just the real numbers or complex numbers or something like that. So this linear kind of resembles the linearity of polynomials. Like if you remember what a linear polynomial is, it looks essentially like this. So let's do some examples of linear things or nonlinear things. So let's say the following. Let's check if the following functions are linear or not linear. Let's look at t squared, the second derivative of y over dt squared, plus t dy dt plus 2y is equal to sine of t. Is this a linear differential equation or a nonlinear differential equation?
I think it's linear.
It is a linear differential equation because each of my, the point is I want to think of these derivatives as my variables. Each of my variables appears on its own. They're not being squared, they're not being multiplied by each other, they're not being put into cosine or whatever, they're just appearing on their own as variables. And then their coefficients are allowed to be any functions of t. T squared is a function of t, t is a function of t, 2 is a function of t, sine of t is a function of t. So this is linear. Now I'm going to give you an example where you should tell me whether it's linear or not. Let's do t squared y dy over dt plus cosine of t times cosine of y plus y squared is equal to e to the t. Is this a linear or a nonlinear differential equation?
Non-linear.
Non-linear.
This is very much nonlinear. In fact, each term has something nonlinear about it. Here, the nonlinear part of this function is that we have a y times dy over dt. This is not linear. We've got two of our variables multiplied together. Here, I'm examining cosine of y. Cosine of one of my variables. Cosine is not a linear function. This is not linear. And then here, I've got one of my variables that I'm squaring. And squaring is also not a linear procedure. So this is not linear. So there's kind of, each of these terms has something that prevents it from being a linear differential equation. And it is 1 o'clock. I can't really tell if these feel long or if they feel short. Probably they feel long for you. I haven't decided how they feel yet to me. Any questions before we go? Okay, have a nice afternoon.
Thank you.
Thank you very much.
Thank you.
Thank you. Thank you.
Thank you.
Absolutely.